you. Well, first of all, good afternoon. And well, before entering the subject, I would like to thank the organizers for their impressive efforts to put together such an exciting program, which remains in these pandemic times quite a challenge. And I'm quite honored that I get this occasion to talk about one of my favorite topics, which is the application of soil and sediment micromorphology in archaeological research. And I propose to start with discussing some basic concepts. And a first question that we can ask ourselves is, what is soil and sediment micromorphology? And if you want to put it in a very simple way, micromorphology can be defined as a study of soils and sediments in an undisturbed state and at a microscopic level. And this has basically two important implications. Because we are studying these samples in an undisturbed state, this implies that all the components, think about anthropogenic remains, think about minerals, organic matter, but also pores, being it earthworm galleries, galleries from ants, or just fishes because of the drying out of the soil, well, they are all kept in the position they had within the original stratigraphy. Like we observed it in the field. And secondly, this also means that there is no selection of particular types of remains. So we do not select any of these types of remains, nor do we concentrate them. Now, how do we perform our study? Well, the first thing that we need are basically thin sections, and these are very thin slices of soil and or sediments. And I'll just show you an example and see if I can go back because I was too quick here. So this is an example of such thin section, and it's basically a very thin slice. When we are talking about thin, it means extremely thin because they have a thickness of about 0.03 millimeter or 30 micrometer. And what else do we need? Well, we do need a microscope. And we do need a specific microscope because we use petrographic microscopes, which are also called polarizing microscopes. And well, they're quite easy to recognize because they all have a turning table, like you can see here. And they also have what we call an analyzer and a polarizer, which are basically two filters that help us to observe typical characteristics of minerals and anthropogenic features. Now, what can we observe when we look into such a microscope? Well, we can basically see the different components that are present. So here, for instance, all these blackish material that we see here are very tiny charcoal particles. We also have some minerals, mostly quartz, these white features that you see here. We also have remains of a floor, a clayey floor here at the bottom. So you see we have all these remains that are nicely preserved in the thin section. But it's not just the components that we can see, but because they are also all kept in their original position, we can also study how the different components are distributed. We can see whether they are concentrated, whether they are aligned, or just randomly distributed. So for instance, here we see that all these charcoal particles tend to be nicely aligned and horizontal to this floor level below. So this is quite an important thing that we can observe. And what else can we do? Well, in an indirect way, we can also get some information about processes. How did the soil form? Is this due to natural processes, or are there particular human activities involved? And this is basically crucial information if we want to understand the soils and sediments that we are studying, and also to make them tell us basically their fascinating story. Now, the first step in our research is, of course, to obtain the right samples. And for micromorphology, we need specific samples. In contrast to, for instance, the study of fruits and seeds or bone remains, we do not need bulk samples. What we need are oriented block samples, because we want to study this original site stratigraphy. And the taking of these blocks, well, is quite simple. What we basically do, the next one, here we are. What we basically do is we select the area that we want to sample, and then we cut out the block. We place a plastic or metal recipient with all the necessary data on it, and what you will see on each of these samples is also an arrow indicating the orientation of the sample, because it's crucial that we know which side is up and which side is down. And well, once we've taken the sample, we will of course have this oriented block. But this block as such, we cannot put under our microscope, and we cannot just cut off a thin slice either, because everything will crumble down. So then we need to perform some preparation of our sample in order to get our thin section. And the first step there is to impregnate the sample with resin, to replace basically all the voids by resin, to obtain a very solid and hard block that we can cut later on. So that's the first step, impregnating the sample. Then we will cut off a new block, a thinner slice that we can paste then onto a glass, and then we will start polishing until we reach this thickness of about 30 micron to obtain our thin section. And in most cases, we will then cover this thin section with a very tiny cover glass, because it's an additional protection of our sample. And well, once we have our thin section, we can basically start our study. And well, of course, in order to describe this microscopic universe, we need some guidelines. How can we basically describe what we see? And well, over the last century, there have been several guidelines that have been developed. And the international standard became the work of George Stokes, of which you see a picture here, who sadly passed away last month. But his guidelines, also sometimes called the White Book, basically permit us to describe all the different components and soil forming features that we can observe within the thin sections. And well, last year there was a second edition of these guidelines for analysis and description of soil and irregular thin sections that came out. But of course, our aim is not to describe, or not only to describe what we see. No, the purpose of micromorphological research in archaeology is to come to an understanding of things we cannot understand based on our field observations. And well, micromorphology has been applied to a series of problematics. First thing is the understanding of the formation of anthropogenic layers, and also everything which has to do with preservation of different components, taphonomical processes. And to get a nice introduction to this theme, I can recommend this green book here, Reconstructing Archaeological Sites by Paul Goldberg and Panagiotis Karkanas. Now, as for what concerns the interpretation of anthropogenic layers and structures, there are the two handbooks by Richard McPhail and Paul Goldberg, the one Practical and Theoretical Geoarchaeology, the other one Applied Soils and Micromorphology in Archaeology, which are also very nicely illustrated. And then when we talk about the application of micromorphology in larger landscape studies, there are some very nice examples in this handbook of Charlie French, Geoarchaeology in Action from 2003 already, I think. Now, a prerequisite to perform an archaeological micromorphological study is, of course, a good knowledge of natural soil conditions. Because what we want to do is basically to detect anomalies which are related to human interference. And a handbook that helps us to understand, A handbook that helps to understand the natural soil development is Interpretation of Micromorphological Features of Soil and Regoliths, which is also called the Blue Book. Now, the themes that have been dealt with over the last decades, well, they are quite diverse. And within the handbook Archaeological Soil and Sediment Micromorphology, which is then called the Black Book, which is like this white and this blue book, basically the three most important reference works for us as micromorphologists. Well, in this book, we get a nice overview of the main research topics of these last decades. And just to give you some examples, there has been quite some work on caves and rock shelters, clearance and pastoral activities, ancient agriculture, traffic, think about roads, but also settlements, occupation surfaces, floors, use of space, combustion features, urban development, thing which is quite interesting is the study of dark air, but also waste management, artisanal, industrial activities, market areas, and so on. And of course, also the interaction between people and landscape. Okay, well, so far I've been talking about the tools that we are using to perform a micromorphological study. And I think that now it's time to go this one step further and show you some practical examples. And the first example I want to show you concerns ancient floor layers. Well, these are often composed of successions of millimeter thick deposits. And I show you here three pictures of this from the Historical Center of Brussels in Belgium. And well, it should not surprise us. The pictures I'm showing are field photographs, because all our micromorphological studies, well, they basically start in the field. It's in the field that we are already defining problematic, and later on we will refine this on the microscope. Now, when we look at it, at first glance, these three pictures show us some more or less identical deposits. But if we're going to look at it on this microscope, we will see that they tell us three completely different stories, and that's what we're going to do now. And all these first layers, well, they correspond basically to a hard feature. We observe in situ burnt material, including the mineral matrix itself that got burned and is affected by these burning events. And what we also can see is what has been burnt, and that's the pictures I'm showing you here. So on the one hand, we see that there's quite some charcoal particles that are preserved, but also a tremendous amount of phytoliths here, grass phytoliths. And what's interesting is that we see that these grass phytoliths are either molten or, like in this picture here below, they do show fluorescence. And that's something that we observed over the last years, is that when you heat phytoliths, they tend to become fluorescent. So that's also quite some interesting feature that we saw here. So this one are the remains of a heart. The next one is showing a completely different story. In this case, we are facing a plaster floor, and you see nicely on this thin section this first layer of plaster, showing also this birefringent pattern. And on top of that, we have these darker colored features, which is basically mostly shard material, finely shard material, and ashes that have been added, possibly to clean as a result of the cleaning of this floor. And on top of that, we see the emergence of a new plastered floor, this one containing much more coarse material. So it's basically the repairing and the reuse of these floors, a whole floor sequence basically that you can see on this picture here. And then the third example is again showing a floor, but this one is a stable floor. So in this case, we do not have plaster, but what we have here is a crust, an orangey crust, which is basically composed of phosphate. So it's basically due to the accumulation of urines and decomposing excrements that created this phosphate crust. What we also see on this picture are all these phytoliths again, these articulated systems of phytoliths from dendritic phytoliths, so indicating that we have some husk fragments also there. So, And we also saw in this section some traces of trampling, and indicating that we really are dealing with a stable floor. So you see 3 different stories, although at a third glance, these deposits in the field looked quite similar. And well, for the last example, I'm going to take you to the historical center of Antwerp. And on this side, also a complex succession of layers was observed, and detailed micromorphological study permitted not only to identify each of these layers, but also to identify basically the sequence. We have ash layers, we have house floors, we have stable floors, basically showing changes in the use of space during the occupation of the site. And I've also chosen this example because it also points to something else: the importance of combining strands of evidence. Here it's especially the integration of data from insect studies and micromorphology that helped us to securely identify the succession of activities that took place basically on one single location. And I will come back later to this potential and importance of interdisciplinary research. Now, I think that these 4 examples can clearly show us the power of micromorphology. It's by changing the scale of observation that we can come to a better understanding of features that are hardly distinguishable in the field. A second theme I want to illustrate concerns basically the identification of ancient agricultural practices. Now, in some cases, the identification of crop fields and gardens can simply rely on historical documents. But if these are absent or not reliable, then we have, of course, to look for other evidence. And well, sometimes this evidence can be quite conclusive. Think about the presence of art, plow, or spade marks, and here you see an example of about 100 spade marks from the center of Brussels. But if we do not have such smoking guns, it becomes, of course, much harder to come to robust identification of these ancient crop fields and gardens. And micromorphology can then be of much help. And I'll show you some examples. What we can do as micromorphologists, we can contribute to the identification of the working of the soil, but we can also tell something about soil improvement, the addition of lime and manuring. And finally, we can also tell indirectly something about the ancient soil fertility. Now, the working of the soil is a difficult one. Sometimes we do find these implement marks, and these are, of course, also smoking guns, like the implement marks that we've seen at the field scale. Other evidence is a bit more difficult to interpret, and there we really need to build up a robust story, because some of the features that we see can have multiple origins. It's what we call equifinality. And this is, for instance, the case with what we call dusty clay and clay silt coatings. Now, what are they? Well, sometimes you will see that the pore get filled in or partially filled in with clay material, but it's not pure clay. You see all kinds of impurities in it, and even some silty particles, some larger particles that got incorporated. And this is due to a surface that got disturbed. You see here an example, such a surface that got sealed off after heavy rainfall. And then you start, of course, with the creation of these kind of filling of the pores lower down. So that's one thing, but we have to be careful, because if an area gets flooded, you can have similar features that are created. So it's always, in itself, it's not sufficient evidence. So we need to build up a story, and then we need to combine it with other evidence. Like, for instance, here, these are fragments of a crust that has been broken down. So that's, again, indicating the working of this soil. Other evidence that we can obtained through this micromorphological study is evidence about soil improvement, because if you are talking about agriculture, then of course the soil has to be kept fertile. And one way to do this is, of course, to add a lot of manure and lime. And evidence for this are, of course, these microscopic coprolites that are sometimes preserved. You see here, it's only 2 millimeter diameter, this coprolite. So with the naked eye, you would not recognize it. And then, of course, we can also sometimes find parasite eggs, which are still preserved, remains of ashes, and, well, the other classics like ceramic fragments, bone fragments, and so on, that can also give us an idea about the enrichment of the soil. Now, something else that micromorphology can contribute to in an indirect way is to identify what has been cultivated on the individual fields. And, well, when we are talking about the crops that have been cultivated on fields, then we are facing a major problem if you want to identify them, because if you're talking about agriculture, we are basically talking about working of the soil, adding oxygen to a soil. And that means that all the organic remains will decompose quite quickly, including the pollen, but also the fruits and seeds. They tend to preserve pretty badly on these crop fields. So this is not the case for phytoliths. Phytoliths are of mineral origin, so they will preserve much better. And so that's one of the things that we've been developing over the last decades, is a method to study these phytoliths in the thin sections. And why in the thin sections? Well, because there we are capable of distinguishing different origins of the phytoliths. Are the phytoliths related to domestic waste? Are they related to manure? Are they related to soil disturbance? Think again of these dusty clay coatings, sometimes even containing phytoliths. Or are they really inside the soil matrix? And these ones are, of course, the ones that are of interest here. And if we do have these phytoliths that have preserved within the soil matrix, then we can also try to get a morphometrical identification. But for this, we do not need only one phytolith, we do need a set of phytoliths. We need a sufficient number of phytoliths, still articulated, so that we are sure that they share a common origin, that they are coming from this one single plant, because otherwise it will become impossible to come to a reliable identification. And if we do have such sets of phytoliths, then we can try to come to this kind of identification. And we managed to get identification of wheat, barley, oats, rye, and emmer for Roman and medieval times in Belgium. And then the last example I would very briefly want to talk about is about urban stratigraphy. When we think about urban stratigraphy, we always think about complexity, because we have this succession of layers, one on top of the other, one cutting through the other, because of continuing occupation for, in many cases, several centuries or even millennia. And another thing which makes urban stratigraphy quite difficult is that we often have very limited windows to observe. For instance, here in this case, we only had a window of about 30 centimeters large to try to understand stratigraphy. So that's one thing. And then we also have these deposits themselves, which can be quite difficult to interpret. We've already been discussing the microstratified layers, think about all these floor layers, but we also have what we call dark earth, which are a bit the opposite. Now, what are these urban dark earths? Well, it's basically very thick, dark colored units, which are very homogeneous, and which are also often rich in human materials, and they also tend to cover large surfaces. And what we have observed them a bit all over Europe, in many towns they are present. And why are they so problematic? I'll show you immediately one example from the center of Oudenaarde in Belgium. What we basically see here in this down part is that we have, looking at this photograph, only one thick dark layer. But if we now have a look at the thin section that has been made from this lower part here, then we see that we can basically very easily distinguish at least a dozen of different layers. And that's also basically the power of micromorphology. We can make the invisible visible. So what's not visible at the field scale may become visible at the microscopic scale. Well, to develop this thematic of urban dark earth a bit further, I will show you the example of Brussels, where we had the opportunity to study quite some dark earth over the last decades. So this is picture, an aerial photograph of Brussels, showing in green the first city wall, in red the second city wall, and in yellow all the observations of the urban dark earth, and the blue ones, the ones we still need to study. Now, why is it important that we study these urban dark earths? Because they are a major source for the understanding of early urban development. Because what happens is that for most towns, the early periods are often poorly documented. So there, the study of the soil itself can become a very important contribution to our understanding of the early development. Further, it can help to record and identify human actions and natural events. It can also help to reconstruct the whole biography of a site, and I'll show you an example of that. And finally, it also contributes to the understanding of the organization of space. First, some practical examples. First site I want very brief to show you is the site of Rue de Boiteux. What did we discover there? Well, we had on top of ancient peat levels, we had a thick dark earth that you can see here. And this dark earth basically testified of ancient horticultural activities. And then we had a lot of implement marks that were preserved. And we also found a tremendous amount of excrements and parasite eggs. And the excrements, or the coprolites, well, they belong to humans. So we basically are able to identify the type of manure that has been applied there. So apparently it was cesspits that have been emptied onto these gardens to make them more fertile. Totally different example, Touranesens, also a site from the center of town. And what we have here we have ancient floor levels, and we do find quite some traces of trampling in them. We also have quite some building materials that are incorporated within this dark earth. And what's important, we have a tremendous amount of bioturbation mixing up it all. So at the field scale, we can't recognize these floor levels anymore, but it's only at the microscopic scale that these features become visible. Now, talking about dark earth, we always want to understand how did they form. And well, by studying so many of these dark earths in Brussels, we were able to come to construct a model on the formation of dark earth. And what we see in this model, it looks a bit difficult at first sight, but everything starts basically with apparent material on which things are happening. And this can be, on the one hand, non-cultural processes. Think about bioturbation and biological activity, erosion, sedimentation, but also all kinds of soil development. On the other hand, you have human alterations, human modifications. Think about the accumulation of material. This can be domestic waste, this can be manure, cess, construction debris, industrial or artisanal waste. There's also the mixing of materials and truncation removal, because people tend sometimes to dig pits, to move material from one place to another. And there can also be compaction because of trampling and so on and so further. And then in the middle part, you can see all kinds of activities that we were able to identify through this micromorphological study. And then eventually we come to this formation of dark earth. But what's important is that this arrow goes the whole way back, because formation of dark earth is not just one sequence of non-cultural and processes and human alterations. No, in many cases it's a succession. It's a sequence that goes on and on and on until the dark earth gets sealed one way or another. Now, talking about the activities, because we are archaeologists and that's still the main purpose of our research, is to try to understand what people have been doing in the past. Well, we were able to identify meadowland, we were able to identify stable floors, crop fields, we also have some gardens, market activities, building activities, soil extraction activities, burials, and artisanal activities, just to name a few of the activities that we were able to identify within the urban dark earth. But it's not just about identifying these activities. Sometimes we can reconstruct the whole site biography just by looking at these dark earths under the microscope. And I'll show you this example of the court of Hoogstraten, which is basically situated, again, in the center of Brussels, next to the palace of Charles V, which you can see here in this picture. And well, the sequence starts somewhere before the 10th century, where we have meadowland. And this meadowland gets transformed into a crop field somewhere between the 11th and the 13th century AD. And on top of that crop field, we then have the construction of a stable. The stable burned down at a certain point in time. And then we have the addition of a tremendous amount of construction debris. It's more than 1 meter of construction debris that has been added. But that's not the end of the story, because on top of this construction debris, people constructed in the 16th century this garden, the garden from the court of Hoogstraten. The garden then got abandoned at a certain point in time, and today everything became part of the museum that you can still visit today. So that here you can see basically the whole story of the site reconstructed through the study of this dark earth. And well, if we put all the data that we were able to obtain through this micromorphological study together, then we can start to create maps that help us to understand how activity areas evolved over time. And it shows some quite interesting sequences for the center of Brussels. Now, if we have a look at the 10th, 12th century AD, the first thing I need to say to you is that this first and the second city hall were not existing at that point in time, but it helps us a bit to orient things. So we see that here we are really in the historical center. But if you look at the activities that are taking place, we see that we have crop fields, we see that we have meadows. So these are more rural activities that are happening in this period. So it gives us a clear view on this period as being mostly still a very rural area. And it's only in this 14th, 16th century that we see this change. Because here, what do we see? Now we have a lot of gardens. We have a lot of construction works. Basically, on every single site, we see that there's construction work going on. We see the appearance of artisanal activities. We see the appearance of market activities. So here we really see this urbanization going on. So now we are really in a very urban area. And this is basically possible to identify only through the study of the soil itself, because of this lack of written sources, especially for these old periods. Now, what can we say now in conclusion about micromorphology? Well, just to summarize up, micromorphology is a study of soils and sediments in an undisturbed state and at a microscopic level. What's also important is that all components are kept in the position they had when samples have been taken. This allows us to identify distribution patterns, relations between components and features, but also to identify processes. We can apply it to the formation of anthropogenic layers. Taphonomical issues can also help us to interpret the anthropogenic layers and structures, and to better understanding of the interaction of nature and humans. And well, another important thing is, of course, this interdisciplinarity. Think about this example, phytoliths, insects, or the combination with the study of insects. Okay, and then one last. Yeah, now, of course, I need to acknowledge quite some people who have contributed to this research over the last 20 years. And well, it's quite a long list. And there's one more thing, one Small announcement on the 31st of March and the 1st of April, there is a third virtual micromorphology meeting. It's also called VIMI. And well, it's basically a meeting of micromorphologists where people can show pictures of certain sections, but where we'll also have a few live sessions, online live sessions, where people are going to show live the study of some thin sections in the microscope. Okay, so I only can thank you for your attention, and if there are any questions, I'll be happy to try to answer them.